Okay, so let's continue here with the array antennas. So before the break, we just learned these things, that this translation here of the antenna element corresponds to the phase shift of the radiation vector. And that is this little object that sits here, which is the same as you recognize from the radiation vector when you looked at the current. Because we can think about the antenna element as a lot of small radiating elements, and then that could be almost an array. So the formulas have to look very similar. Okay, so now we will use these ones. And now we will then look at pattern multiplication for this. And that is really the introduction of the array factor. So let's say now that you have your antenna. You have some coordinate system here. You have some antenna element here, another one there, and a third one here. And I call now the vector that points to the first one as D0, and then D1, D2. And that can, of course, be n of these. And now in each of these, I assume now that there's hit a current density, and that is A0, J0. And then here I have A1, J1, A2, J2 in some ways. And what I assume in these cases is that actually these currents have the same shape, but the coefficients here can change. So the coefficient here really means what kind of signal are you sending to this antenna element? What kind of amplitude and phase do you send to it? How much should you translate, or how much should you delay this signal, and how much should you amplify it? But the shape of the current on the antenna will be the same, because that is determined by the antenna element. So I have here a lot of positions. I have feed coefficients, and then I have the current densities, Jn, which is meaning it is the same shape, it just translated in space. And then what we precisely did is to determine the radiation vectors from all of these current densities, and we saw that they could depend on some element pattern, like some original current density times this amplitude shift that I have An, and the phase due to its position. And if I have that now for each of these elements, I can just use that the radiation vector is linear in this, so I have superposition. So the total radiation vector from all of these elements here, I get as a sum of the individual radiation vectors. And this element pattern here sits in all of them. So that means I can basically move that outside of this sum, and I can call the rest of this an array factor, and that is an element pattern that I have here. So the array factor here only depends in these cases of the positions. So when I look at this array factor, it doesn't really matter what antenna element it is. It's the same thing for a dipole antenna, for a patch antenna, and so on. I can take a horn antenna I have here. It doesn't affect this part here. That only affects this one here. So the element radiation vector. So now I separate the construction of the array into one piece that says design your antenna elements, and the other piece which says define your array, which means have the elements put at the right position and give them the right weights that sits there. So I separate these two pieces, which of course is very powerful, because the antenna element here, you know, you have to design it, you have to know the length of it, is it resonant, it has an impedance, it has a lot of properties to the antenna in some ways. The array factor then is only the geometry of the array. And how should I send my signals to that array to get the correct main lobe, side lobe levels, direction, and so on. And that is this array factor. And when we talk about arrays in this course, it's basically about the array factor. And then we can get the total radiation pattern by doing this multiplication. So you multiply the pattern from your array with the pattern from your antenna element. That gives you the total radiation pattern. So, array factor. So if we do the analysis now of an array antenna with array factors, it's really divided into two pieces. So the first piece here is to analyze the element radiation pattern. So that can be the radiation pattern from dipole, loop, patch, helix, whatever antenna. And that you have learned how to do, because that's what we've been doing in the previous 6 lectures. That is to take that individual element, determine how does it radiate. That is the radiation pattern from that one. And you remember you took this radiation vector we just had, and then you remove the radial component of that. Then you got the element radiation pattern. Then you have to do a second step, and that is to get the array factor from the position and excitation coefficients of each element. That is the array factor. And if we see the drawing here, the first one here, you recognize as a Hertzian dipole, this donut shape. So this is now a Z-directed Hertzian dipole that has that pattern. And now I did an array factor by taking here 2 different elements, so plus minus, quarter of a wavelength in the X direction, which means that I said one element sits there. I should probably change the color. Maybe, I don't know what color is good here. Black is probably good. One element sits there and one element sits there. So they are on the X-axis, and there is half a wavelength between them. And this is now the plot of the array factor from those 2. I will show you how to plot this and compute this very, very soon. And now if I would like to know the total radiation, because what it means here is that here it sits 1 Hertzian dipole, here it sits 1 Hertzian dipole. What is the total radiation pattern? To do that, I do multiply the previous ones. So I take my array factor, I have to square it to get the power, and I have to take my element pattern, so the array, radiation vector squared. And if I multiply them, this is what I get down here. So of course you can now try to do this in your head. So if you think about multiplication of these 2, that pattern to that one, of course this one has a 0 in the Z direction. And if you multiply anything with 0, you get 0. So there should be no radiation there, which you can see there is no radiation there. If you look at the radiation along the Y-axis, the array factor is strong, it has its maximum there, and the element pattern is strong in the Y-axis. So of course the total product is also big in that direction. If I look in the X direction out there, I can see my element pattern radiates in X, but my array factor do not radiate in X. That's equal to 0 there, and that means that there is no radiation in the X direction either. And here I've just multiplied those together, and this is the pattern you get. So this is this principle of pattern multiplication in these cases. And the assumptions of this are important. So the question I got just before, that we have to neglect something. And what we do neglect here, we assume is negligible mutual coupling. So we don't really assume that these antenna elements talk a lot to each other. We assume they're really separate antenna elements, and it's sufficient to analyze this apart from one. That is one of the really fundamental assumptions that we have. We will look at that a little bit before. And as I mentioned before, previously we have investigated these element radiation patterns, which means that now we're going to study the array factors. So that's what we're going to do now for the rest of these array lectures that we have. So I got a question here from Ilyas, I think. Common radiation space results between the 2. I'm not sure I understand your question precisely. Can you clarify it for me?
Basically, the multiplication of the 2, the array factor and the Hertzian dipole, gives us a more directed lobes, right?
In this case, yes, it does.
Okay, I was just trying to understand the concept of the multiplication.
Yeah, so you can think about it almost like the pointwise multiplication. So if you think here about the element pattern, you can see here, if you go into some certain direction there, you get some amplitude of this. And the amplitude is basically go out there and gets how long is this distance from the center to the shape of this 3D pattern as you have there. It's also given in the color scale. So red is the strongest, yellow a little bit weaker, green weaker. And that's the distance that you have here. This is the longest distance, so the strongest radiation, which means it radiates more power in that direction. The same thing for the array factor, but due to the geometry. So if I look here in the y direction, I have something proportional to this. It's a long distance, so that's a lot of power. If I go straight up, I have the same amount of power. But if I go some angle here, I can go an angle out there, I have a lower power. And then I multiply in the same point or same angles for the element pattern with the array factor. I multiply those together. And of course, I get a new number, and that is the number that is plotted down. And that means that if this one is 0 here, as it is there, this one has to be 0 straight off, because if you multiply something with 0, you always get 0. And the same thing, you go in the x direction, you go x out there, this is also 0. And then you have something strong there because this one is strong and this one is strong.
So it basically, the multiplication gives us this, the common space, the radiated space between the two products, right?
Yeah, I don't know common space, the name. It gives the total radiation pattern for the array antenna. So the radiation intensity from the array antenna.
All right, thank
you. So it's really this one, watts per angle that comes out from this array, where you then have feed to both elements. So you send some power to both elements. And what is the power that radiates out from that one? And how is it distributed in different, in different angular directions? That is what comes out. Okay, let's continue with that, and we will actually calculate these things for some array antennas. So let's look first at the single element, so not really an array, or an array with only one element. And now the difference here with the array factor from what we had with the element pattern is that these are not vector components. So this is like sound. It actually propagates isotropically. So the phase here of a single isotropic point source is just the propagation distance. That's everything that sits there. So if you think that you send a signal, so in this drawing up here, I say now that I send a signal here that is 1 from the center. So it has phase and amplitude 1 in the center. If I then move a distance lambda out, this one will again have the value +1. Because you are 1, you move one wavelength. One wavelength is 360 degrees, so you're back where you started. It's like a sine function out. So again, it is 1 when you come out there, the phase of this one. But if I only go half a wavelength, so I sit between these two, so I go there, then I have moved 180 degrees out, and that means I have a phase or an amplitude signal there, which is -1. So that is this propagation distance that comes out there. So it is in some ways periodic with lambda. You go lambda out, you repeat yourself when we look at the phase of this one. The radiation pattern, of course, for a point source is just isotropic. So it's a sphere out with the same value everywhere. Not very interesting from an array. But of course, an array then we get by adding up 2 of these together. Yeah, so this is the radiation pattern of this point source. So now if I take 2 point sources, so I do 2 of these now at the same time. And I say that I send the signals with the same amplitude and phase, both from the blue one and the purple one here. And after time 1, again, they propagated a short distance out. After time 2, they propagate a little bit longer, a little bit longer. And what we can see now is that if you follow a line out here, you always get constructive interference. So if you sit on a line out from this, the distance to that line is as long from the blue and purple one. So when I continue out here, they're always on that dashed line. So that means I should add up the 2 signals on that line. I have constructive interference. That is what we will see from our arrays, that if I send the same amplitude and phase, let's say in the Z-directed dipole like this, I have a broadside radiation. It radiates outside from that structure. It radiates away from it due to this constructive interference, because the distance is the same when you sit on a line between. So that is in some ways an interpretation we have. If I want to know what's happening in a point somewhere up here, then of course I have different phases of these ones. So some might contribute with one number, another one with the different numbers, and I have to add them up, and I get a lower than the total sum with just the amplitudes. So if we look what's happening in this case then, so let's say again, I send a signal from this 1, 1, and if I go in the theta equal to 90 degrees, so that means that I go out now in this direction here, then I have equal distance, equal phase, so I add up everything constructively in this case. So I basically get the signal 1, 1, I will get in some ways a sum of those two that radiates out. If I instead want to radiate this now at say 60 degrees, then at 60 degrees I sit far out here, and then it's always a little bit closer to this element than to this element. And the distance there is this part plus this part. So d over 2 cosine theta times 2. So d cosine theta. That is the distance difference between those two. And then if that is equal to pi, it's destructive interference. I get a null. If it's equal to 2 pi, I will get again constructive interference. And now the distance between those two, if I say it's short, it will be a lower number, and I will get less radiation in that direction. If I continue up here, I just get a new distance between them. And if I go to the end fire direction of this, then I have the total distance, which is this one between them. So if you think you sit here as a receiver, of course, it's always closer to this one than it is down to that one there. And the distance between them is this distance here, which is d in this case. And then if d is lambda over 2, and you send the same signal, it's 180 degrees phase shift, you get a null in this direction. So that is in some ways the way of thinking about how you should add up the patterns. So if I now draw the patterns in these ones, this is the pattern we get from those two point sources there. We will calculate it on the next slide. And of course, if I go in 90 degrees, I have the maximum radiation, because the distance here is this distance that comes in here. That is the largest distance inside. This is the radiation pattern in polar coordinates. If I go in 60 degrees, I get lower radiated power, because now I only get this distance here. So this is the radiation pattern that sits there, which is lower than that it was for pi over 2 or 90 degrees. And of course, if I want radiation in 30 degrees instead, I have almost no radiation instead, and that is due to this difference that I come in now, that it's closer to this point than this point, and this case is a lambda over 2, and it's almost a lambda over 2 between those two, so almost destructive interference. You get very weak radiation, much weaker than you had here, because of course this distance here is much less than this one here. That is what the radiation pattern shows. And if I go to 0 degrees, I have no radiation at all. I have destructive interference, because the phase difference between these two is then the distance from there to there. And that was lambda over 2, and lambda over 2 is 180 degrees. And that means that one send in that case 1, and then plus minus 1, and that equals to 0. So I can just add up those two ones that are sent there. So that means I get no radiation in that part, which also the radiation pattern here shows, because it has no amplitude at 0 degrees. So that is my array factor. So now let's take these cases here and compute the same thing. So we take these two isotropic point sources. We say we have equal excitation. So lambda LAN is 0.5. Lambda over 2 spacing. And that means that I put the positions as I had before let's say plus minus quarter of a wavelength in the Z direction. That's what I put down. And now I'm going to compute what is then the radiation pattern or the array factor for this one. So that means that I can take my two array factors. I have my excitation coefficients, half, that is the half that sits there. So that is this AN. And then I have a sum over these terms, and I just have to sum in where is the first one and where is the second one. And that is the part that we have D1 there, that position of that one, and that is D2 there. And then I have to write in what is that D1, what is the D2 in these cases. And doing that, I have this R hat, so the direction I'm looking times the direction where my element is Z, and that is equal to cosine theta in this case. So here I get in a cosine theta. And then I can see that what I have in these cases is two terms. I can sum them up, and the result of this one is that it is cosine pi over 2 cosine theta. So that is the radiation pattern of this one that is drawn over here. So that is the one I have there. That is the drawing of these ones. That's it. So that is how that one looks. And you can see again now, if you put in that theta is equal to 90 degrees. So let's say that I'm looking in this direction here, then theta here is equal to 90. Cosine 90 degrees is equal to 0. And then you take that times pi over 2 is still 0. And then you take cosine 0, that is equal to 1. So that is the maximum value that you have there. If you put in 60 degrees instead, you get a different value, and then you get this length that comes in there, because you get then cosine of 60 times pi over 2 and cosine of that, and then you get the number or the length that comes out there. And if you plug it in for 0 degrees, so if I go straight up in these cases, then I have that cosine theta is equal to 1, and then it's cosine pi over 2, which is equal to 0. So then you have the 0 in that 0 degrees that sits there. And this is exactly the same pattern that we saw before. So that is the array factor from these 2 point sources for sources that are lambda over 2 from each other. So we can see that we have destructive interference in the Z direction. And the interpretation of this, even without the calculation, is just that the lambda over 2 spacing between those is 180-degree phase shift. And then you can say that I send plus from this, I send plus from that, but the distance between them is lambda over 2. And then in every point out here, you get destructive interference. One of them is +1, the other one is -1, and the sum is 0. When you go in this direction, there is always constructive interference. So you get a strong pattern when you go out in the broadside direction. They add up in that way, and they cancel each other in the upside direction and Z direction. So that is both the interpretation and the calculation of this array factor from these 2 point sources. So now let's use that and then figure out here, how should you feed 2 elements which are spaced lambda over 2 if you want maximum radiation in the Z direction? And I know I should have done this as a poll, but I didn't in this case. So think about it. If you now again have this same spacing as before, they are in the Z direction. So one antenna element sits there, one sits there. The distance between them is lambda over 2. How should you feed them to get a lot of radiation straight up? How should you feed the 2 elements? In the previous case, we fed them with 1, 1. So the same phase of them. Then we had a destructive interference going straight up, so no radiation goes straight up. Now I want radiation straight up, which means that I have to now compensate for this lambda over 2, that is 180 degrees. I want to have constructive interference. So basically what I have to do is that I have to add another 180 degrees. And if I would do that, I have 360 degrees. So if I add another piece there, then I will get 360, which means that I need in these cases that one is 1, and 1 is -1. So +1 from 1 and -1 from 1. 180-degree phase shift from the elements. That's it. And then 180-degree phase shift from lambda over 2 spacing. Constructive interference, 360 degrees radiation straight up. So that's how we can change the phase of this to make them radiate in different directions. So exactly what I mentioned there, the distance lambda over 2 is 180 degrees. Add an additional 180 degrees, you get 360, which is 0, and you have constructive interference in the z direction. So I should send now +1 from this one and -1 from that one, or the opposite, it doesn't matter. The absolute phase is irrelevant for these cases. And then I get this radiation that is constructive in these cases and destructive in this direction. So there is equal to 0 in this direction. So no radiation in the XY plane, radiation in +z direction and -z direction from this one. And of course I can calculate it. So if I pick these elements now, one as +0.5, one as -0.5, exactly what I had before, but now with a minus sign between them. And the minus sign there change cosine to sine when you add up these exponents. So this is sine pi over 2 cosine theta. And if you look at the values there, you can see it straight up, it's equal to 1. And in the XY plane, theta equal to 90 is equal to 0. So no radiation in the horizontal plane, all radiation straight up, just by changing the phase of the elements. So I can make it radiate in different ways. Then, of course, I need an antenna element that also radiates that, because in the end, I should multiply with the element patterns too. This is only the array factor that we do. So, do you follow these pieces here? Is it difficult or is it hard? Yeah, or is it simple, I should mean. Not difficult and hard. What do you say? Do you follow the thinking in some ways that space, separation in space is of course a phase difference depending on what direction you go. So you have to look at the distance in the direction you are radiating or interested in the radiation. And then that the wavelengths is in some ways one wavelength 360 degrees, half a wavelength 180 degrees, which is a phase shift from +1 to -1. And then I can compensate that by adding a phase shift in the elements, and then I can get the radiation I would like. Okay, one comment came, not much. So that means we have to practice more on it. So in some ways, if you compare with what we did before with the radiation vectors, it was more complicated because there we had the current that also had a direction. Now we skip that. Now we're only putting at distance from one point to distance in another point. So slightly simpler than the radiation vector. But we also focus more on it because here we can actually control these signals. So if you have an array antenna, what you can control is these things. You can control what phase you send into it. And by sending in a different phase, you can change the radiation pattern from going like in this direction to suddenly go in that direction after. You can control where you beam though. And that means that you change the phase because the phase you send to the element is added to this distance in that direction you are looking. And you have to take care of both. Then you get the total array factor, which then gives you a radiation pattern that comes out. Okay, so we will hope this gets clarified. If you have questions, ask them. So otherwise, I will just move on. We have another 50 minutes and we'll go through some more cases of these array antennas. So now let's look at what happens with the distance between two dipoles again, or 2 point sources. So we assume again that we have two of these isotropic point sources. So we have the array factor. We feed them again with 0.5 and 0.5. So maximum radiation always in the broadside direction. Constructive interference always in this direction. We can compute the array factor, and it's exactly what we had in the previous case, but now we also have the distance measured in them. So there we have this KD. So if I increase the distance, KD is increasing. If KD is equal to 0, this is just cosine of 0, and it's 1. So if the distance would be very small here, it will just be equal to 1 in these cases. When I increase the distance, and now it's 0.2 lambda, you can see it's not really isotropic, it's slightly shifted. So more radiation in this direction and less radiation in this direction. If we go to our next case, is what we had before, which was this lambda over 2. We got this nice pattern in some ways, a little bit similar to the donut shape that we had before. But now comes the interesting case. Let's move up here in these cases in wavelengths here. So lambda over 2. Now I go to 2 lambda. What happened there? Not 2, this is 1 lambda. So this is this case here. So here is equal to lambda. Now I have constructive interference both in this direction and this direction. So it radiates both up and to the right. And of course also down and to the left here. It's rotationally symmetric when you go around that. So it always will radiate in this direction. This is the broadside radiation. And that's because you have this one, 2 identical, same phase on both elements. So it always radiates in the broadside. But now the distance between the elements is lambda. And lambda is 360 degrees, which means it's actually constructive also in this direction. And if you now start increasing it even further in this case, so now I put it on 2 lambda instead. What's happening now is you get radiation there, 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 and there. So now we start radiating in many places. And that's because you get constructive interference in many, many different directions, because the distance between them is now several wavelengths. And when you have several wavelengths, you get what's called grating lobes. And that is that you don't have a main lobe, you have many lobes with the same amplitude. In almost all antenna cases, this is bad, but there are exceptions to it. If I make it even higher here, you can see it gets more and more of these lobes in different directions, these grating lobes. If you think about what we talked about today, in which case have we seen this large distance between antenna elements? If you think back about examples I showed you some radar antennas, I showed you some communication antennas, and then I showed you radio astronomy antenna with these parabolic reflectors and told you that the distance between them could be 10,000 wavelengths. This is 8 wavelengths. So imagine how that array factor look like when you have 10,000 of those. That will basically be covered here between rays all over the place. So the array factor is incredibly, incredibly, what to say, sharp for this one. And now we think, what is the interesting part? That's a total radiation pattern where you multiply this with also the element pattern. And by doing that for this radio astronomy, you actually can shoot out that you only take like 1 of this. And that is why you can get such a sharp pattern from that one. That is this pattern multiplication. And it's something that's called also an interferometric measurement. So you have many wavelengths between them, you're looking at the interference pattern between them. And that's why you can get very high resolution on them. When it comes to typical communication and radar antennas, this is where you sit. You never want to have that for these cases of antennas. To actually design them where you have these grating lobes is incredibly problematic and hard for almost all cases. So you want to have a certain direction of radiation. There are cases where you can go up to this and you can then have an element pattern that cuts away this. And then you can have slightly larger distance between them. But you are really stuck and you would like to be there. That is your ideal case and the case we will focus on. But of course, as I mentioned, there are exceptions. When we now do arrays, we would change the plotting of them and we will start plotting almost everything in dB scale. So we would do it in the dB scale, so 10 times the 10 logarithm of the power that comes out. For these patterns, it doesn't change much, except for this lower one here that now almost looks like a circle in some ways, depending on what range we have for the dB scale. But we will see that we will use that for many cases. So if we now do our 1D array and we take more elements than 2, then I just have to sum up many elements. So my array factor here, if I have elements now at position ZNND, and I say now that I have some coefficients A on them. So that means I have to sum all of these up. So I have to sum up the coefficient times this phase factor. And we do that in some ways for the z direction. And if we do it in the z direction, we get this cosine theta. And a convenient way here is actually to drop all that is common in these cases here. Not the d in these cases. We add everything that is common in these cases here, and we introduce what's called a digital wave number, which is kd cosine theta. So the wave number times the distance, and then cosine theta, so the angle where we're looking at it. And then we can see here that our array factor is the discrete Fourier transform of these coefficients. So it's very similar to what we had before with the radiation vector. I said that's basically the Fourier transform of the current density. When we have an array, it's the Fourier transform of the signals we send to it instead. So here we can Fourier transform this an to it. And then we actually get out, in these cases, the array factor. So the same thing sits behind this. But since this is discrete, yeah, it's a discrete Fourier transform that can come out. We will not use that very much, but it is one connection that sits between them. And if our array would be now in a different direction, for example, the x direction instead of the z direction, I can just change this digital wave number, because it just says what are the angles that comes in for these cases. And that we can then compute for this in the x, y, and z direction, and that comes from the formulas that we have used before. So that is what theta and phi that comes into these cases. And that means that when we write it in this digital wave number, it all looks the same. It doesn't matter if the 1D array is in x or y or z direction. In most cases in this course, we will do it in the z direction because it's slightly simpler. So now let's do what is our first array. So we will do a uniform 1D array. And uniform means here that we have the same amplitude of all the coefficients. And we will start with the same phase of them too. And we let them have just the positive phase. So an is equal to 1 over n. So these are the coefficients that we have. And if we do that, I can write up my array factor. And then I should just sum all of these exponents. If I call them z, yeah, then I can sum them up here. It is, I think, geometric series that we get in these cases. I can simplify it, and if I simplify this one here, I plug in what I get my final results here. So this is now the array factor from an array with n elements where all of them have equal amplitude. And the phase is not interesting for these ones because we want the radiated power. So if we take the absolute value, only this piece exists. So this is the array factor for a uniform array with now an radiation in some ways in the broadside radiation. So all of them have the same phase. And if we take a look at these ones, we will see what it looks like. We can plot them here. So if I take this array factor and I just plot the amplitude squared on those ones, so the power that comes out, we can see up here, this is the case with n equal to 2. So 2 elements in a dB scale that sits here. I think it's 20 dB range for these cases. And you can see like a donut type pattern in some ways. When we now start increasing the number of elements, so if I go to 3 elements, you can see something's happened now. I still have a main radiation here. But now I got some radiation actually in the zero direction. So why do I have, when I have 3 elements, why do I get radiation in the z direction? You can figure it out from what we learned here, because we say that we have now 3 elements, 1, 1, 1. 2 of those are separated, or all of them are separated lambda over 2. So in the z direction, 2 of them will always cancel each other, and you get contribution from 1 of them. So you get radiation from basically 1 point source in the z direction. That is what comes out there. And if I now increase it to 4, now you can see side lobes showing up. You can see here the beam width gets more narrow. So the beam gets more narrow. and you start getting some side lobes that's picking up here. And the higher I go here from n equal to 5, 6, and 7 elements, you can see it's all the time got a narrow beam. So the beam is decreasing when I increase the number of elements. And also the number of side lobes are increasing when I increase the number of elements. So the number of side lobes 1, 2, 3, 4, 5, 6, that's increasing when I increase this number. That is the effect of adding more of those. And this is what's called a uniform array. So there is no really tapering of it. All elements have the same amplitude. And in these cases, we've seen that we could have different distances, and then we can have different elements that sits there. If we look what's happening in these cases, we can see that our array factor is periodic in 2 pi periodic in this digital wave number. So we can actually compare that with sampling of a signal if we would like to. We can say we have a visible region, which is our theta, it's between 0 and pi, and that corresponds to that our digital wave number here is plus minus kd. It is in that range. So if I now look at these cases, I can compare it with the Nyquist criteria for sampling. And if I have this specific case here of lambda over 2, that's basically 2 sample points per wavelength in these cases. So this is the Nyquist sampling of these ones. And this one up here is in some ways a distance that is smaller, is in some ways, I would say, oversampled in some ways. There's too many data points. And if you go on the opposite side, it's undersampled. And from sampling, you know that it's good to be in this perfect Nyquist range or around that at least. And it's the same thing here. That is this lambda over 2 case. And that's typically where we want to sit with our arrays. If D is increasing, we can get these grating lobes. We have missed some part of it. And the beam width, we have not talked about beam width before as our parameter. We talked about directivity and so on. And the beam width measures how wide is the lobe in some ways. So a typical version is the half power beam width or the -3 dB beam width. So if I plot here the array factor, I have the maximum here, go down to half the power. So these distances are the same. And then I can take the beam width that sits between those. If I do the same in a polar plot, yeah, then I'm there. So how wide is this beam? And the maximum radiation, of course, is down here. That is the same as I had there. So if I read off this number and I read off the angle, there is the same. These are 2 different ways of plotting the same thing. And so that says that if you go outside of this beam width, you lose at least more than half of the power if you use half power beam. So that is one quantity that we actually have not talked so much about before, but of course it's a good parameter to describe these antennas and these arrays. Okay, we will very soon end up this, and we will actually come back to these examples later on. I will not go through it here, but we will of course look at a lot of different type of antennas, and reflector antennas is one type, and you're going to design your own reflector antenna. And one type is actually what you can do with a corner reflector. You will also do this in the exercises. And we can see that these type of antennas, in the same way as antennas above the ground plane, can be analyzed as arrays. So if I take these cases here and I say I have now a reflector here. So this is some metal plane. You can think about it as this perfectly electric conductor. So metal, copper or something, very good conductor. And then in the middle of these ones, I put a dipole. So the dipole sits between those walls in some ways. And if I draw a picture from above, then again, I have the walls that sits here. This is one wall that sits there. And I find my antenna elements here in the middle between those two. And now I can figure out, okay, how does this radiate? Because now it has a radiate with respect to these walls and so on. And now we can use image currents for that, because this means that I will have an image current there, which is -I. I have one minus there, that is -I, and I have one back there, that is +I. And then I actually have 4 current sources. and that is an array. And 2 coefficients is the same, and 2 coefficients are minus the same. And that will actually form a simple array, which we can analyze, and we can easily determine the radiation from these ones. And yeah, that is what we do here. So in some ways, you can see here the image currents that we will have in these cases. And if I take those image currents, I can add up what is the array factor, and I can compute the array factor from these ones. And from that, I can then determine easily the radiation pattern. I can multiply with the element pattern, for example, Hertzian dipole, and I can get out a fairly nice radiation pattern from this one. We have to time, so I do this quite fast, but we will come back to this example. And in some ways here in the end, you could see the radiation intensity that then comes out, a fairly complicated formula, but easy to throw into MATLAB or something. And here is one example of the radiation pattern that comes out. And imagine in the third lab, you're going to build your own reflector antenna. So we will talk a lot about reflector antennas later on, but this is a pretty good antenna, and it has pretty good radiation properties. In these cases, we got a directivity of approximately 11, with fairly easy design rules of saying that the distance here should be approximately lambda/2, having a dipole as a source. Okay, so that is actually it for today. Time is out, and this was in some ways the first lecture about array design or array antennas. On the next lecture, we will really look at different type of array pattern design. So how do we synthesize a radiation pattern that is good? In most cases, we would like to have a radiation pattern that doesn't have high side lobes, for example. How can we make the beam narrow and the side lobes low? How can we formulate that? How can I make the beam go in a certain direction? How do I do beam steering? That we'll do on the next lecture. And then in 1 week time, we will continue with more array design. And in that case, we will actually look at also situations where, we do 2D arrays, MIMO arrays, and so on, more complicated versions from these ones. So that's basically it for today. We have an exercise coming up also on Wednesday,